Okay, so let's start our lesson for today. So before I start, I do want to make one tiny correction from our notes from yesterday. I made a tiny typo and no one caught it. I think you guys were maybe upset about power series. But I'm just going to scroll down to where I spotted the mistake last night. Uh, so, so the mistake was right here. So I put the background dark because I think it's better for my eyesight because I'm having some irritation in my eye because I've been teaching since 9 a.m. so it's tough. Make it here at 6 p.m. it's kind of tough for me right now, but I made it, so let's hope we will make it for the remaining days. So first thing, let me tell you the correction. So if you go back to your notes from last night, I said the definition of a power series is in the such form: the sum starting from n equals 0 to infinity, an x minus x naught to the nth power. So that's the definition. And this series is centered at x naught. Okay, so we like to center x naught equal to 0, not 1. Okay, so that's the mistake I had last time. I put 1 by mistake, but it shouldn't have been 0. Okay, so that we have the following summation: an x minus 0, which is x naught, to the n equals some an x to the n. Okay, so that was the only mistake I saw, but hopefully everything else is okay. So any questions on that? Okay, so again, please speak through your audio if you're able to. It's much faster for me to communicate with you. So today we're going to start by, I'm going to give you what's going to be on our quiz for next class. So if you look at the calendar, next class, the quiz we're going to have is going to be our last quiz for the semester. So it's almost over. Pretty exciting, but it's also sad that soon we're not going to see each other and no more differentials, right? After July 20th, you move on to another course or whatever you do, but we're not gonna do this anymore, sadly. So let me give you what's gonna be on quiz number 4. This is our last quiz. So, right, sadly, that's the last quiz. And then, well, the quiz is going to be on sections. So we got test. So 3.7 spring mass, 3.8. So that's together, and then we did 4.2, 4.3, 5.1. That's today, and 5.2. So these are the sections for our next quiz, and I'm planning to give you 30 minutes for this quiz. So it's going to be a bit longer. So let's make this 7:40 to 8:10 p.m. So you'll have an extra 2 minutes extra, so with 2 minutes, so that would be 32 minutes. But by 8:15, I think it will close up. I think that's how I will set it up. So let's time it for 8:10 for now. So that's full 30 minutes. Any questions? Did I not mention? Oh, 4.1. No, that's just the theoretical stuff with the nth order. We can skip that. Yeah, ignore it. Yeah, we don't have to worry about that one. Okay, cool. So that's for our quiz. Any questions? Okay, so if there are no questions, let's continue what we are supposed to finish for today. So I'm going to go ahead and give you an example of how to find radius of convergence and interval of convergence by using ratio test. Okay, so that's where we're going to start today. So let's look at, well, I gave you an example yesterday and I didn't finish. So let me just copy that same example. So I'm hoping you had a chance to look at it, but if you didn't, let's just follow through. No big deal. So copy and paste. Okay, so here's the problem from last night. So we're still continuing with 5.1. So this is still 5.1. Okay, so we want to determine the radius of convergence for this infinite sum, and it's a power series. So to find the radius of convergence, we're going to apply ratio test. So the ratio test is to take the limit as n approaches infinity in absolute value a sub n plus 1 over a sub n, and we want that to be restricted. So I'll show you the restriction as we go along. So our a sub n is going to be the summation that's given to us. So we know a sub n is just the original summation, so that's x plus 1 to the n over n times 2 to the n. That's a sub n. What is a sub n plus 1? What do you guys think? Yeah, so you just replace n with n plus 1. So this sequence is going to be x plus 1 to the power n plus 1 over n plus 1 times 2 to the power n plus 1. So that's what the a sub n plus 1 represent. So let's plug this into the definition. So we're going to take the limit as n goes to infinity of, so we have a sub n plus 1, that's the one that I just wrote down on the bottom, x plus 1 to the power n plus 1 over n plus 1 times 2 to the n plus 1. Now, by dividing it by an is same as multiplying by its reciprocal, okay? So I'm going to times it by n times 2 to the n over x plus 1 to the n. So I multiplied by the reciprocal of an. Alright, so now let's simplify before we take the limit. So this is all just on the side. So we have the limit as n approaches infinity of, so I can cancel out x plus 1 to the n and x plus 1 to the n. So I can cancel out one of these factors. So I'll be left with x plus 1 to the 1 power. So one of those left. And then 2 to the n, I can also cancel with 2 to the n. So I'm going to have 2 to the n on the 1 on the bottom. So that's 2 to the 1. And then we're still left with the n on top over n plus 1. So that wouldn't simplify. Okay, so just more algebra. Well, now we're ready to take the limit. So you're taking the limit only on n. So that means x is treated as a constant, right? It's not relevant to the limit. So we are going to pull out the expression x plus 1 in absolute value and then apply limits as n approaches infinity of, and I can also pull out the 2 as well. So that also comes out because it doesn't involve an n. So we're taking the limit of n over n plus 1. And let's see what this is. So what is this limit? So as n goes to infinity, what is this limit approaching? Right, so you can think of it as when the degrees of the top and the bottom are the same and you're approaching infinity, then it's the coefficient in front of them, right? That's what we learn in calculus. So coefficient in front of n is 1, and coefficient in front of n on the bottom is also 1. So this limit approaches 1. So we have in absolute value x plus 1 over 2 times 1 because the limit is 1. And now we want to restrict this. We're going to apply the geometric series where it says if this is less than 1, then we have convergent, right? That was the rule we wrote down yesterday. So we want this to be less than 1 strictly so that we can find radius of convergence. So that means we have in absolute value x plus 1 over 2 is less than 1. So if I split up this absolute value, we have negative 1 is less than x plus 1 is less than 1 over 2. So that's the inequality we're going to solve. And then to solve this, we're going to go ahead and multiply by 2. So we have negative 2 is less than x plus 1 is less than 2. And then by subtracting 1, we have x is between 1 and negative 3. So that's the interval of convergent. So interval of convergence. So you can think of this as the diameter, right? So if I were to draw a picture for you, so here's negative 3 and here is 1. So this power series will converge within this interval. So somewhere right here. So how do we find the radius of convergent? Yeah, so this is sort of like the diameter, right? So to find the radius, we just call it radius of convergence because it's fancy, because it is the radius of convergence. So to find the radius, all you do is you add them up and divide it by 2, right? So we have, so the diameter is what? It's going to be 1 minus negative 3. So you add them up, you get 4. So that means the radius of convergence, which we're calling a rho, it's going to be d over 2. So that's 4 over 2, that's 2. So the radius of convergence for this particular power series is 2. So any questions on this problem? Okay, let's try another one. Go ahead. Oh, you said no, okay. All right, so let me do another example. Very quickly compute the radius of convergence. So you do have to find the diameter first, and then we divide that by 2 to get the radius. So why not, right? So here's another example. So find the radius of convergence. So I'm just abbreviating ROC. Hopefully you guys can follow that. Of the summation n equals 0 to infinity of x minus 3 to the n power. So again, we're going to set up the ratio test. So let me give you a few seconds to process. So then I'll start. So by using the ratio test, we have the limit as n goes to infinity of an plus 1 over an. We want this to be less than 1, right? So that it converges. So let's figure that out. So we have limit as n approaches infinity of a sub n plus 1 would be just x plus 1 to the power n plus 1 over a sub n, that's just the original series, x minus 3 to the n power. Okay, now again, simplify. So x plus, wait, I think I wrote something wrong. Doesn't look right. Yeah, yeah. Thank you. Looks so weird. Okay, so minus 3. Now that looks right. Phew. Okay, so I can cancel one of the factor of x minus 3 to the n, so I'll be left with the limit as n approaches infinity of x minus 3 to the 1 power. That's what we're left with, because one of the factor would cancel, so this one with the n will cancel out. So what will this simplify to? Well, let's take the limit. So x minus 3, it doesn't involve n, because that's where we're applying limit to. So I can just pull it outside the limit. So we have, in absolute value, x minus 3 times the limit as n approaches infinity of just a constant 1, right? It doesn't have anything involving n. So what's the limit of a constant 1? Just 1, right? Limit of a constant is always a constant. It doesn't matter how large n is. So cool. So we have x minus 3. We want that to be less than 1 in absolute value, so that we can have convergence. So now by applying some algebra, we split this up. We have x minus 3 is less than 1, less than negative 1. So that means x is going to be less than, so you add 3 to both sides, that's 4, and less than 2. So hopefully I did that right. Yeah. So this is the diameter. So what is the diameter as a value? What is d? Right? It would be 4 minus 2, that's 2. So that means the radius of convergence is going to be rho, which is d over 2. That's 2 over 2. It's 1. So that would be the radius of convergence for this particular series. Okay. So very briefly, we reviewed the ratio test. Hopefully you can go through the problems from the textbook after we did these problems. Okay, so now I'm going to go ahead and show you how do we express a function as an infinite sum. So we're going to use the idea of a Taylor series. Hopefully that name sounds familiar. Taylor series. Right? Okay, so that sounds good. So Taylor series. So Taylor, what is the formula that Taylor gave us? So let me just write Taylor's formula instead of Taylor series. Okay, so we know that, so we have a formula that if a function f of x is continuous infinitely many times, we can then express it as, well, as a Taylor series. So just a second. So as a Taylor Okay, now what is that? What is that Taylor series? Well, it says if you have a function f of x, you can express it as a sum n equals 0 to infinity of f to the nth derivative evaluated at x naught over n factorial times x minus x naught to the nth power. That's the famous formula for Taylor series, or I like to call it the Taylor's formula. So why not, right? So if you compare this with the power series we had earlier, the definition, we said we can express a function as an infinite sum of n equals 0 to infinity of an x minus x naught to the power n. If you were to compare both of these formulas, they're almost the same, right? Almost, except if you look closely, this part right here in front of x minus x naught to the n is where you'll get all the coefficient. Your an is the coefficient, and this is the formula for finding all the coefficient. So that's one way to think about. So that looks like a big smiley face. That's one way you can compute the coefficient of a power series, which we're going to do in 5.3. Okay, so I'm going to come back to this again, but right now we just want to know, can we express any function as a Taylor series as long as they're continuous infinitely many times at some x naught? That's the idea, and the answer is yes. So I'm going to show you one example how to do it. Hopefully you'll have a general idea how it's done. So we're just going to hold on to this thought that an can also be computed by this Taylor series formula, where an is equal to f to the nth derivative evaluated at x naught over n factorial. Okay, so let's write down another remark. So here's a remark, and then we'll do an example. So say the function f is continuous, right? So that means it has derivatives of all order, right? That's what it means to be continuous. That means you can take its derivative as many times you want. So if we say f is continuous and we're expressing f as an infinite sum, which is n equals 0 to infinity of an, and so for simplicity I'm going to use x not equal to 0. Okay, so x to the n power. So what I did was I'm using x naught is 0 so that the computation is simpler. So hopefully you can follow me through this. So let's write out some of the term for f of x, and then we're going to differentiate this respect to x. So if I write out n equals 0, we have a0, x to the 0, that's 1, plus if n equals 1, we have an, x to the 1, plus n equals 2, a2, x to the 2, plus n equals 3, a3, x to the 3, and so on, right? It's an infinite sum. So we just wrote out the first 4 terms. Now we want to take derivative of this. So we want to take derivative of f. So because it's continuous, you can take derivative term by term, right? So I'm going to go ahead and differentiate. So if I take the derivative of f, that means I can take derivative of this infinite sum term by term. So a0 plus a1 x plus a2 x squared plus a3 x cubed plus so on, right? Let's differentiate. So we have f prime is what? What's the derivative of a0? 0. So that disappears. What about a1? So a1 of x, good, so that's a1, plus what about a2x to the second power? Right, so you use the power rule, right? And right, so and then you have 3a3x squared, and you can guess the next one too, 4a4x to the third, and fill in the rest, right? Okay, I don't need that bracket. So that's the expression we have for the first derivative. Now if I were to write this in a closed form, because you don't want to write this every time you're doing a problem, we want to come up with formulas. I can write this as a sum. Now this summation will start from n equals 1, because the 0th term disappeared, right? a0 went to 0. And then it will go up to infinity. What about the rest? The rest is going to be n times an x to the n minus 1. This is the usual rule. So you can also think about this formula from up here, right here. So I think it's really hard for you to see what I'm highlighting. So I'm highlighting f of x, the summation part. If I were to differentiate this summation, I can do it term by term, which you just saw, but I can also use the closed formula to differentiate. So what I do, I bring down the power n, and then I subtract 1 from the power. That's the power rule. So that's how we got this formula right here that I'm just highlighting. So hopefully you guys can follow through. So that will be an expression for the first derivative. Now can you guess the expression for the second derivative? What do you guys think? What will be the second derivative? Exactly. So you just bring down the power. So an n times n minus 1, an x to the n minus 2. So you got the idea. And then you can find the third derivative in a closed form instead of writing out term by term. But the idea is, yes, you can differentiate these term by term as long as they're continuous. And because we're working with power series are continuous everywhere. So they're nice. Okay. So these are the important functions or the derivative we're going to remember for 5.2. So keep these in mind. So f of x is going to be that, and then f prime of x, it's going to be this expression, and one more. And we also need second derivative because we will be solving second order using power series. So we're going to need the formula for second derivative as well. So the second derivative will be this expression. So let me know if you guys have a question. Well, I didn't finish writing the summation. Where does it start? The second derivative. So it's going to start at 2. Okay, because when you differentiate f prime, a1 will go to 0 because it doesn't have a variable. So it's going to start from a2. Okay, so having said that, let's do an example using Taylor's formula to find a Taylor series for a continuous function. So let's do that right now very quickly. So let's compute Taylor series for f of x equals cosine of x. Very familiar function, right? We've seen it. And I'm going to center at x naught equal to 0. You could center anywhere you want, but 0 is just nice. That's why. Okay, so let's see. So using Taylor's formula, well, it says f of x is equal to the sum starting from n equals 0 to infinity, f to the nth derivative, evaluated at x naught over n factorial. So if I'm looking at the first derivative when n is equal to 1, we're going to write f of first derivative evaluated at x naught over 1 factorial. If I'm looking at the second derivative, it will be f raised to the second derivative evaluated at x naught over 2 factorial, and so on. So first we're going to let n equal 0. Well, that's f to the 0th derivative, meaning it's the function itself. You didn't take any derivative. So when n is equal to 0, it's just f of x itself. So we have cosine of x, and we're going to evaluate at x not equal to 0. Okay, that's the first term. So this is going to be cosine of 0, which is 1, right? Cosine of 0 is 1. Now let's look at n equals 1. So that's first derivative. N equals 1 will give us the first derivative. So let's compute the derivative of cosine. That's negative sine of x. And then we evaluate it at x naught equals to 0. That would give us negative sine of 0. That's 0. Okay. And then n equals 2. That will be f to the second derivative of x. So this derivative of the first derivative is going to be negative cosine of x evaluated at x not equal 0. So we have negative cosine of 0, which is negative 1. So let's go for a few more terms because the second term disappears because of 0. So let's go ahead and do a couple more. When n equals 3, we're looking at the third derivative of this function. So taking the derivative of the second derivative, that would be cosine, no wait, hold on, sine of x. And evaluating this at 0, we have sine of 0 is equal to 0. So you can kind of see the pattern, right? You have 1, 0, negative 1, 0. Next one, let's hope it's going to be 1, right? So if n is equal to 4, we're looking at the fourth derivative of x. That would be cosine of x evaluated at x not equal to 0. So that gives us cosine of 0. Oh, that's 1. Perfect. Okay, I think we have enough term. We have 5 terms, right? So let's write it out. So Taylor says, so using Taylor's formula, we know f of x is expressed as an infinite sum, starting from n equals 0 to infinity, f to the nth derivative evaluated at x naught over n factorial times x minus x naught to the nth power. So let's write a couple of terms for this infinite sum. So when n equals 0, we're looking at f to the 0th derivative. So it looks weird to write 0th derivative or no derivative. So it's just, let me just say 0th derivative. Okay, so it's not the power 0. It's the 0th derivative, meaning the original function itself. The original function evaluated at x naught over 0 factorial times x minus x naught to the 1 power, plus now the second term is f prime evaluated at x naught over 1 factorial x minus x naught to the 1 power. Oh, this is to the 0 power. Sorry, I missed that power. And then let's write out a couple more terms. Plus f to the second derivative evaluated at x naught over, so maybe I should write it this way, guys. So instead of writing 0th derivative, it's just f of x, right? So it's the original function. So we keep that as f of x. I feel weird writing 0th derivative term. Okay, so back to the second derivative, 2 factorial. And then we have x minus x naught to the second power. So I'm going to write a few more. Plus third derivative of f of x evaluated at x naught over 3 factorial x minus x naught to the third, and so on, right? So you got the idea. So let's plug this in. In our case, we're expressing cosine of x. So f of x is cosine of x. It's going to be the first derivative evaluated at x naught, so that's n equals 0. We got 1, right? So that will be 1 over 0 factorial x minus x naught to the 0 power, that's just 1. Plus, now the second term is going to be the first derivative evaluated at x naught. So that's right here when n equals 1. That's the first derivative evaluated at x naught. It's negative sign of 0. That's 0. So we have 0 times x minus x naught. So it's going to disappear. Second term, well, the third term, the second derivative. What is that expression? So that's right here. Negative 1. So we have negative 1. Negative 1 over 2 factorial x minus x naught to the second power. And then next term, the third derivative, we got 0. So that's going to be 0. And then fourth derivative, so I didn't write out the term, but you can see the fourth derivative will be over 4 factorial. So fourth derivative, we had 1 over 4 factorial times x minus x naught to the 4th power, and so on. Okay, so we fill in these coefficients that we just computed as we differentiated this function 4 times. Okay, let me know if you guys have questions. So now let's simplify this. Well, in our case, we're centering x naught to be 0. So I'm going to plug that in as well. So we have cosine of x is equal to 1 over 0 factorial, that's just 1, minus 1 over 2 factorial. X naught is 0, so this is just x squared. Next term is also 0, so that disappears. Plus 1 over 4 factorial times x minus 0, so that's x to the 4th, plus so on. So that's the famous formula for cosine expressed as a power series. Now, there is a closed formula for this. Can we come up with it? We can also write this in a closed formula. N equals 0 to infinity. So you see the pattern, it alternates, right? So you have plus, minus, plus. You know the next term that comes after x to the 4th will most likely be minus. Well, it's going to be 0, the 5th power, then the 6th power is going to be minus. So we need a negative 1 to the nth power so that it gives us the negative alternating sign. What about the bottom? Looks like we have even factorial, right? You have 2 factorial, 4 factorial. Next, you can guess it's going to be 6 factorial. So I'm going to go with 2n factorial. Hopefully that will work. So we're going to check. What else? Now, what about the x? X also has the even power, right? We had 0, 2, and 4. So we can say that this is x to the 2n power. Now let's check. Does it work? So if n is equal to, so let's check this. Does this work? If n is equal to 1, right? Let's see. If n is 1, we have negative 1 to the 1 power, x to the 2, because n times 2 is 1. And then on the bottom, we have 2 factorial. Is that true? Yeah, check. Check. It works. And you can test the next one. If n is 3, you should get the 1 over 4 factorial over, if n is 2. If n is 2, n is 2, you'll get this term. So n equals 2 will give you this formula. And then if n equals 0, you'll get this formula. So that will be the closed form for cosine of x. Any questions on this? So this is the Taylor series expansion for cosine. So you can try out sine and e to the x if you want to test your knowledge on Taylor series. Okay? So that's that. Any questions? Go ahead. Right, so we also give this a name. If you center at 0, you can call it Maclaurin series. But in general, all of these are Taylor series. Yeah, but when we center at 0, it's very special, so we give it a name, Maclaurin series. But in general, if x0 is not 0, then we just call it in general Taylor series. So I'm just keep calling it Taylor, so I didn't want to bring in another name. But good point. Thank you. All right, so any other questions before we move on to 5.2? All right, so if there are no questions, let's move on to 5.2. So 5.2 is very important for us because we are going to be seeking power series solution near ordinary point for second order. Okay, so series solution near ordinary point. So this is part 1. So there is also part 2, that's 5.3. Not so important, but this is the one that you want to highly remember. You must remember. So, well, let's see. So what kind of form are we looking at? So we want to solve. So now we want to find power series solutions for second order linear differential equations. Homogeneous with now not a constant coefficient but a function coefficient. Coefficients. So our coefficients could possibly also be functions, and we know how to deal with them now. Okay, so that's the goal. But if you have constant coefficient, you can also do it. But why if we already know how to do characteristic polynomial idea, right? So we're going to keep using the characteristic polynomial idea if we have constant coefficient, but if we have a function coefficient, we're going to do by power series. That's the best method to go by. So let me give you some examples that we're going to work with. So you might encounter examples such as, examples like, so these are very famous one. I think this one is one of them. Xy double prime plus xy prime plus x squared minus r squared times y equals to 0. So you see how the coefficients of our dependent variable is now x squared minus r squared. So they're all functions. And this equation is very special because it has a name. It's called Bessel Equation. So very special equation. And then we also be doing something like this one, x squared y double prime plus xy prime plus well, let me bring in some real constants. So x squared y double prime plus beta xy prime plus gamma y equals to 0. This one we're going to be solving later in the future This is called Euler Equation. And this is going to be in 5.4. There was a section in 3.4, I believe, where we talked about Euler. I didn't cover that. We're going to cover it in 5.4. So after 5.4, you can go back and do 3.4. It will make sense. Okay, so you can do that when you have some time. So these are the type of equation we're going to work with now, where the coefficient is a function and it's a second order homogeneous. So let's look at the general form. Okay. Come again? Okay. All right. Testing, testing. Can you guys hear me? Okay. All right. Thank you. So let's look at this form of the differential equation that we're going to be solving. So this is the form we're going to be working with. So suppose you have a differential equation, some p of x times d squared y over dx squared plus some function q of x times dy dx plus r of x times y equals to 0. Let's call this equation 1. So that's a kind of function we're going to be working with. So let's define what is an ordinary point, okay? Because we want to find solution near ordinary point. So definition. So a point x0 is ordinary if when you plug it into the function p, which is the coefficient in front of the second derivative, it doesn't equal to 0. That's what it means to be ordinary, okay? Very important. So if it's ordinary, that means I can go ahead and divide the entire differential equation by p of x because it doesn't equal to 0, so we can have a general form. So that's the next thing we want to do. We want to take the differential equation and divide both sides by p of x. Okay. So any questions so far? So are you guys following me so far? Okay. All right, that's good to hear. So let's do that. Let's divide the entire equation 1 by p of x. So we have the following. If we do that, we have so this would now become d squared y over dx squared plus q of x over p of x dy dx plus r of x over p of x y equals to 0. So we're only allowed to do that if p evaluated at x0 is not 0. Okay? So just to simplify the notation, we're just going to rename these functions. So we're going to rename this as a little p of x and let this as a little q of x. Okay? So that means our differential equation, and I'm going to rewrite the derivatives using the prime notation. So we will have y double prime plus some function p of x y prime plus q of x times y equals to 0. So that's the form we like to use, and it's just much simpler than looking at p of x over q of x, q of x over p of x, r of x over p of x. So it's just much more confusing. So this is the form that's nicer. So what are we going to assume? We're going to assume that the solution to this second order differential equation is power series. Okay? So that means we're going to assume that the solution form is a power series. So we have y equals the infinite sum n starting from 0 to infinity an x minus x naught to the n power. That's what we're going to assume. It has this form as its solution. Okay, that's the closed form. If you want, you can extend it out. Now let's choose. So let x naught be 0, an ordinary point. Okay, so if that's the center we're looking at, that means we can simplify our assumption. Y is going to be the sum from n equals 0 to infinity an x to the n. So that's the formula we're going to be working with. It's just much more simpler when you use center at 0. Okay, and for this course we are going to be using center at 0 all the time. So, and then if you also want to look at the extended form of this, meaning writing out some of the terms, this is a0 plus a1x plus a2 x squared plus a3 x cubed, and so on. So our goal is to find all of these unknown coefficients, a0, a1, a2, a3. So that's the big question. What is a0? What is a1, a2, and so on? That's the big question, because depending on the specific differential equation, depending on the initial condition, these values will vary. Okay? Alright, so let me do an example. Hopefully that will tie everything in together. Let's look at a very simple case, something that we already know how to solve by writing out its characteristic polynomial, but we're going to use series solution to come up with the same solution. Okay, so that's what we're going to do first. So the first example that I'm going to work on, so let's find a series solution of the equation y double prime plus y equals to 0 using x naught equals to 0. Okay, so we're going to write a solution to this second order differential equation using power series. Okay, so the same idea, you assume the solution form, you compute its first derivative, second derivative, plug it in. That was the usual method. That's what we're going to do. So we're going to compute its first derivative. So we know the solution form, it's going to be this power series, y equals the sum n equals 0 to infinity an, and because x naught is 0, so we can just use x to the n, because x naught term will drop. If that's y, what's y prime? What's the expression for that? Right, so that's what we derived right here. That's what we needed that for. We saw if f of x is that, we're calling it y now instead of f of x. F prime, y prime is going to be this box we had earlier, and then the second derivative is going to be the last box. I have it here. So let's rewrite those. So we have the sum starting at n equals 1 to infinity an x to the, I think I just forgot something, n times an x to the n minus 1, and then the second derivative is going to be the sum starting at n equals 2 to infinity n times n minus 1 an x to the n minus 2. So we have an expression for the first derivative, second derivative, and y. Let's plug those in. So let's plug in y and y double prime, because our equation doesn't involve y prime, so we don't need that, into original equation. Okay, so if we do that, we get the sum n starting from 2 to infinity n times n minus 1 an x to the n minus 2 plus y. That's going to be n equals 0 to infinity an x to the n equals to 0. Okay, so that looks neat, right? That looks neat. Not so bad, because it only has 2 terms, so it's not really much. But the idea is the same. If you had more terms, you'll be plugging in more variables, and it's just more work to do very carefully. Okay? Now, the next thing you want to do is to use the properties of summation that we talked about in 5.1. I can join the two summation together as long as they have same indexing, meaning they start at the same lower limit. So the first one starts at 2, the second one starts at 0. That's a problem. Okay, let's ignore that for now. Second thing is, I want to also put them together having the same power for x. So if you notice, the first one has a power n minus 2 for x, the second one has n. So we're going to come up with the substitution so that they both have same power for x. That's the important step. We need to do that. Once you plug them in, match up their power. So step number 2 is to come up with substitution. So for the first summation, I'm going to let k, so I'm going to use k, is equal to n minus 2. I'm going to let that to be k. And then for the second summation, I'm going to let k to be n. And you'll see that will do the job. So first one, we're going to use k equals n minus 2. And second one, we're going to use k equals n. If we do that, well, what do we have now? So look at what we have. Question? Oh, right, you can change. So each summation will have its own substitution. Yeah, so we're allowed to do that. So for the first one, so I'm going to write everything in terms of k. So if k is equal to n minus 2, so our summation will now become the following. So if n is equal to 2, k is going to start at 0. Because so I'm solving this for n. So we have k plus 2. Okay, yep, this is good. So now, if n is equal to 2, k is going to be 0. If n is infinity, k will also be infinity. So the upper limit is okay. Now, so what about, so just give me a second. So it looks like I'm having difficulties right here. Just give me a second, guys. I don't know what's going on. Okay, it's working now. Alright, sorry for that few seconds break. So the first term on the summation, we have n. Well, n is going to be k plus 2. So we have k plus 2. So this is not good. Let's do it again. So n is going to be k plus 2. And then n minus 1 would be k plus 1. So, sorry guys, I'm having some difficulties with my stylus. It's not writing for some reason. So why don't you guys fill in the rest while I figure this out? So just plug in k for n and see how does the summation looks like while I figure this out. Okay, let's hope it's gonna work now. Sorry guys, I don't know what to do. It's not working well. So for n minus 1 we have k plus 1, and then a sub n, well, n will be k plus 2, x to the k, that's what we wanted. And for the second summation we have, if n is equal to 0, k will also start at 0 to infinity, a sub k, x to the k equals to 0. Neat, right? So now that they both have x to the k, and also they both start at the same summation, k equals 0, I can join them into a single summation and factor out x to the k because that's common. So we have the following summation. So we have the sum from k equals 0 to infinity of k plus 2, k plus 1, a sub k plus 2 from the first summation. And for the second one, we have a sub k, everything times x to the k equals to 0. Okay? And now we're going to equate the coefficient. Okay? So we can solve for what's the formula that we can come up with to find these coefficients. And we're going to call that formula recurrence relation. So you can think of on the right side, you have 0 x to the k, right? So that means x to the k cannot be 0. That means the coefficient has to be 0. So we're going to let the coefficient of x to the k on the left side to equal 0. So we have k plus 2, k plus 1, a sub k plus 2, plus a sub k equals to 0. And once you're in this stage, you want to solve for the highest subscript. And among these two terms, our highest subscript happens to be this one right here, a sub k plus 2. So we're going to solve for this term, and that will give us the recurrence relation that we're after. So we have a sub k plus 2 is equal to negative a sub k all over k plus 2 times k plus 1. So that's our recurrence relation. So this is what we call recursion formula or recurrence relation. So any of these are the same synonyms. So now we have a formula to find our coefficients, right? So we're looking for what are these coefficients. If we assume we have a power series solution, we want to know what is A0, what is A1, what is A2. Well, we find them from the recurrence relation. So we almost have the solution out. So let's write it out. So our solution is going to be y equals the infinite sum n starting from 0 to infinity, an x to the n, and I'm going to write out just few terms so you see how the solution looks like. A0 plus A1 x plus A2 x squared plus A3 x cubed, and so on. So let's find these coefficients using the recurrence relation. So from the recurrence relation, you want to start off from k equals 0, okay? So you don't want to pick any negative value for k. You want to start from 0 up to as many terms you want to write out, but start from 0. You don't want to pick negative value. So if I like k to be 0, we get a sub 2, because k is 0. So that would be negative a sub 0 over 2 times 1. So that would be negative a sub 0 over 2. And if I like k equal 1, we have the coefficient a sub 3. That would give us a sub 1 negative over 3 plus 2, 3 times 2. So that would be negative a1 over 6. Let's go for one more. If k equals to 2, we have a sub 4. That would be negative a sub 2 over, what do we get? 4 times 3, right? Now, so remember, this is a second order, right? It's a second order differential equation. That means you're supposed to have only two unknown constants. Before we had C1 and C2 were the two unknown constants, right? And here we're going to pick A0 and A1 to be our only unknown constants in the solution. And everything else you want to express them either using A0 or A1. So that's what we're going to do. Now, see, I have A2 expressed as in terms of A0, so that's fine. A3 is expressed as in terms of A1, that's also fine. But what about A4? Well, that's expressed as A2, but we can't have another constant other than A0 and A1. So we're going to substitute what was A2 from the beginning. Well, we found A2 happens to be negative A0 over 2. Let's plug that in. So we have negative, negative, that's positive A0 over 2 times 4 times 3. So you want to express your coefficient always in terms of two unknown constants, A0 and A1, because it's a second order, only two constants are supposed to be unknown. Alright, so any questions up to here? And you can go ahead and find more terms if you want to, but I think we have the general idea. So let's look at the solution. Y is equal to A0. We found that to be negative A0. Wait, sorry, I'm writing things that are not supposed to be written this way. We never found what A0 was, right? When we start picking value for k, we only got to A2. That was the first coefficient we found. So we're going to let A0 be A0 and A1 be A1. And then the rest, we're going to use this computation that we just computed a few seconds ago. So A2, that was found to be negative A0 over 2. So negative A0 over 2 x squared. That's A2. And A3, we found it to be negative A1 over 6 x to the third power. And then A4, so we want to one more. That's A0 over 2 times 3 times 4 x to the 4, because that was the fourth A4, so that will be x to the fourth power, and so on, right? Well, now I'm going to put them together using A0s together and A1s together. So let's pull those out. So we have y equals A0 times, so the first one involve A0, that's 1. The third one involve A0, that's minus 1/2 x squared. And the fifth one involves A0. So that would be 1 over. Now, if you recall, 2 times 3 times 4 or if you rethink it in a reversed order, 4 times, so 4 times 3 times 2, that's just 4 factorial. Do you guys remember that? Right, so I'm going to write over 4 factorial instead of 4 times 3 times 2, and the next to the fourth, plus, of course, there are more terms. Now we're going to group the terms involving a1. So a1 times, so the first term that has a1 is x, and then the next term that has a1 is negative 1 over 6 times x to the third. And there's probably more that I didn't write down, but that's totally fine. So that's the solution to the power series. That's the solution to the second order in power series. That looks long. That looks pretty long. But you know the nice thing about this problem? That we know the closed formula for these infinite sum. So look very carefully. I'm going to rewrite it a little bit more. So this can be written as 2 factorial. What about 6? How do you rewrite 6 as a factorial? Yeah, right. So I'm going to rewrite that as 3 factorial. So that way you can recognize this as one of your famous memorized power series. But up to here, this is done. Okay. For a test, this is done. Now we're just going to go 1 extra mile just to give you a better understanding that we know how the solution looks like. It's a familiar function. So if you recall, you don't need to recall, let's just scroll up. If you look at my previous example that I did in green, so cosine of x. You see how this is ooh. So it looks like my answer got erased somehow. This was x to the 2n, right? X to the 2n over 2n factorial. Okay, so what do you notice? Do you notice that cosine of x is the infinite sum of 1 minus 1 over 2 factorial x squared plus 1 over 4 factorial over x to the fourth? Do you see that appearing here? Right? So you should, this is cosine. And what about this one? So I didn't prove this to you. You can guess, right? This is sine of x. So you can say this solution is a0 cosine of x plus a1 sine of x in closed form. That would be the most beautiful solution to this. But the series solution is nice too. It just has so many terms, but they're nice. So, well, now let's backtrack a little bit. We were solving which one? We were solving this differential equation. Constant coefficient. That means you don't need power series method to do this. You can use the characteristic polynomial. So y squared plus y equals 0. Right? So let's show that on the side. So this is side note. So y double prime plus y equals to 0. How do you solve this from chapter 3 knowledge? So, okay, good. And then what are the roots? Right. So we know how the solution looks like. It's y equals c1 cosine of t plus c2 sine of t. Isn't that wonderful? So we got the same answer, but we took the long trip, right? We went all the way around and we still got to the same destination. So that's the nice thing about power series. You get the solution, but it just takes you a little longer. But some questions, like with function coefficient, we don't have a characteristic polynomial to them. We have to go through this procedure that we followed for power series. So that's why this is important. Okay, so any questions on this? How do you guys like the method? Okay, anyone else want to share their opinion? Yeah, right? So it's okay, so we have some positive and negatives. Oh, that's life, right? That's part of life. Let me write down the steps first, and then I will do another example where we have to use this method. We don't have choice. So let's write down the steps. What were the steps we took to find the solution to that, right? So let me write down these steps for you. So here are the steps. So first, we make the guess. So we guess our solution form. It's going to be y equals the infinite sum an x to the n. Now let me tell you this in advance. You don't have to keep track of the index. You can ignore that. In fact, you can completely ignore the indexing. Okay? So instead of keeping track of n equals 0 to infinity, just use this one, the sum. It doesn't matter where it starts. Ignore them. An x to the n. Go with that, and you'll see you still get the same answer, and it saves you some time. You don't have to worry about shifting the index. So that will save us some time. For this problem, it was nice because when we make this clever substitution, k is equal to n minus 2 for the first summation, and k equals n for the second, we kind of had the summation both starting at the same point after that point. So that was okay. We don't have to rewrite out any terms for any of this summation. But in the future, you might encounter where they don't start at the same point, so you have to write out some of the terms. To avoid that, we're just going to ignore the indexing. So hopefully that makes sense. I'm going to do an example where I don't keep track of the index, but we still get the same answer. So it's not a big deal in this course. But maybe in your other courses, it might be a big difference, okay? So for this course, it's okay if you ignore indexing. This second part is once you guess that's the solution form, an expanded form will be a0 plus a1x plus a2 x squared plus so on, right? That will be the expanded form. Then we know that y prime is going to be this expression, the sum, again ignoring the indexing, n times an x to the n minus 1, and we know the second derivative is replaced with the sum n times n minus 1 an x to the n minus 2. Okay? Well, after we plug them in, what did we do? We try to fix the power for x. We want to make sure that x has a power to the k for all of them. So step 3 would be to fix the powers of x. So we want x to have power of k for all. Okay, so for all x's, you want the power to be x to the k. And then you can put them all together. Step 4 is to combine into a single summation and find the recursion formula, recursive formula. So sometimes it's also called recurrence relation. Okay, So both of these words means the same thing. Recursive formula, recurrence relation, they mean the same thing. Once you have your recurrence formula, we can find the coefficients. So now compute few coefficients depending on what the question is asking. So you can find 3 terms, 4 terms, just find few, A0, A1, A2, so on, right? As many as you want, or as long as it's mentioned in the question. And then the last step would be to just write out the solution. Okay. So let's do a nice problem. So here I have a question that I copied it earlier from one of the final exam. This is going to be long, so let's do this. So you'll see that how the questions are worded in a final exam. I think this was from fall 20 something. Fall something. I don't remember really. I think it's 2011 question mark. So this was one of the question, number 4 on a past final. For this given differential equation, compute the recurrence formula for the coefficients of the power series solution centered at x not equal 0 and use it to compute the first 4 non-zero terms. So they just want first 4. That means you want A0, A1, A2, A3. Those are the first 4. If any of them are 0, then you have to go for few more, okay? Because you want non-zero terms. So that's the key. That's the key to this question. Well, let's do the first part, okay? So now you see how many terms this series has. It has 1, 2, 3, 4, 5 of them. So pretty intense, but we can do it. We just need to learn how to speed up. So let's do it. So we're assuming that the solution form is y equals the sum. Again, I'm not keeping track of the indexing. It's okay to ignore them here. An x to the n. So that means y prime is going to be the sum n times an x to the n minus 1. And y double prime is going to be the sum n times n minus 1 an x to the n minus 2. Now let's plug this in. Now, before you plug them in, I encourage you to do this. Distribute. If you have more than one term, distribute them first and then plug in the derivatives summation form. So we have 3 y double prime minus x y double prime plus x squared y prime plus y plus xy equals to 0. I distribute it. Now I can plug in my notation for each term, y prime, y double prime. Okay? So let's do that. So we have, emergencies outside, so. Okay. All right, so we're back. So we have 3 times y double prime, so that's going to be the expression n times n minus 1 an x to the n minus 2. Second term, we have minus x times the sum starting from, well, we're not starting from anywhere. Sorry, I forgot that I'm skipping the indexing part. So second derivative, that's n times n minus 1 an x to the n minus 2. Now I'm on the third term, plus x squared times y prime, that's going to be n times an x to the n minus 1. And in the fourth term, I have plus y, that's the sum an x to the n. And the last term, I have x times the sum of an x to the n equals to 0. So I carefully plugged in the expression for the derivative. First, second, and y. So that's how it looks like. So you should have 5 summation. 1, 2, 3, 4, 5. Okay. Okay. All right. So now what I'm going to do, I'm going to combine the x's first before I start doing step number 3, where I'm fixing the power. So what do you want to do? So on this stage, what do you want to do? You want to push these inside the summation. So I'm going to push this one inside, and then I'm going to push this one inside, and I'm going to push this inside as well. So I can have a much more simplified power for x if it's relevant. Most likely it is relevant for this question. So if I push the 3 inside the first summation, we have n times 3 n times n minus 1 an x to the n minus 2. Okay, minus. Now what happened as I push the x inside the second summation? So you should notice this. This one, x to the n minus 2, and this one. You can put them together by laws of exponent, right? Right, so you add 1 to the power, so it becomes n minus 1. So we have this sum from n times n minus 1, an x to the now power n minus 1. Because of one extra x that you pushed inside, it subtracts from the negative 2, so it becomes n minus 1. And then for the third one, as I'm pushing x squared inside the summation, it will get modified with that one. They get modified. So what will that exponent be? So yeah, right. So we have this sum n times an x to the n plus 1 plus the second to last doesn't have any, so it's just rewrite. And the last one, what does it become as I push the x inside? Good. So alright, so we finished bringing in the coefficient inside the summation. Well, now the next thing is our step number 3, where you want to have all the x's same power. So I want this to have, oh, that's so, can you guys see that color? It looks so dark. Can you guys see it? Yeah, right, okay, so, yeah, okay, let's not use that. Yellow, okay. Better? Is that better, guys? Yeah, okay. So I want all of these to have same power, which is x to the k. So that's what we're going to do. So we're going to pick a substitution for each one of them so that we have x to the k at the end. So let's do that. So for the first one, I'm going to let k be the exponent, n minus 2. Second one, I'm going to let k be the exponent, x minus 1, n minus 1. Third one, I'm going to let k be the exponent, n plus 1. And this one, I'm going to let k be n. And this one, I'm going to let k be n plus 1. And then we're just going to rewrite everything in terms of k. There are no more n in the picture. And then we can get our recurrence relation. So we're almost done. So thanks to heaven, we're almost done. Okay, so how is that going to look like? Let's see. So the first summation, as I substitute k equals n minus 2, well, this means n is going to be, what is n going to be? Yeah, so let's substitute these in. So we have 3 times k plus 2, and then k plus 1, a sub k, n is k plus 2, so k plus 2, x to the k. We wanted that, so good. Minus the sum. Now for the second, we have, if n is k, if k is n minus 1, n is going to be k plus 1. So we have k plus 1, no, hold on, sorry. I think I skipped a step. So we have n, that's going to be k plus 1. And then n minus 1, that's just going to be k. And then we have a sub k plus 1 x to the k. Plus the next summation, we're going to have k equals n, so that means n is going to be k minus 1. Okay, so what is that going to give us? We have k minus 1, a sub n, that's k minus 1, x to the k. And this one, n is just k, so this is nice. A sub k x to the k. And the last one we have is a sub n is going to be k minus 1. So that would be a sub k minus 1 x to the k equals to 0. So carefully, we translated everything that was in terms of n into k variable. Well, now is the good part. We put them all into one summation and factor out x to the k. So we have the coefficients together. So let's do that. So we have the sum, all the coefficients. So the first one is 3k plus 2, k plus 1, a sub k plus 2 minus k times k plus 1, a sub k plus 1 plus k minus 1, a sub k minus 1 plus a sub k plus a sub k minus 1, everything times x to the k equals to 0. That looks pretty. That's a lot of hard work, but it's pretty, so it's good. Well, now we have our recurrence, almost. For the recurrence, we're going to take the coefficient in front of x to the k and set it equal to 0. And we're going to solve for the highest subscript. Our highest subscript happens to be this piece right here, the one I'm shading in green, but it doesn't shade anymore because my screen is dark. But that's the one you're going to solve for. So we're going to move the others on the left side and then divide it by 3k plus 2 and k plus 1. That will be the recurrence relation. So final step for the coefficients, we have a sub k plus 2 is equal to what? So we have, see, if I move all of these terms to the other side, I get positive k times k plus 1, a sub k plus 1, minus k minus 1, a sub k minus 1, minus a sub k minus a sub k minus 1, all over the coefficient of a sub k plus 2, that's 3, k plus 2, and k plus 1. And you can simplify this. We can simplify only the a sub k minus 1 because we have two of those on top. So if I were to simplify, just take a little bit further, we have this coefficient, and then I'm going to put those together, so that will be minus k plus 1 minus 1, they cancel out, so it's just minus k a sub k minus 1 minus a sub k all over 3 times k plus 2, k plus 1. That will be your simplified recurrence relation. So any questions up to this? So once we have found the recurrence relation, we're almost done, right? So all you have to do is find how many non-zero terms. So they already give us initial conditions. Now keep in mind that the first initial condition is for A0. And the second initial condition is for A1. I'm going to show you these next time, why the first one is always A0 and the second one is always A1. I will show you that next class. So we'll finish this problem next time. I'll write out the coefficients, show you how to plug in the initial condition. We'll have our final solution. Okay?